Good morning. Welcome to our webinar today, Reduce the Risk of Turbine Corrosion and Expensive Repairs with Sodium Monitoring. I'm Dominic O'Donnell, Marketing Director for Swan Analytical USA. In a moment, I'll introduce our speaker, Randy Turner. But first, let me take a minute to familiarize you with our webinar interface software. You should see a control panel similar to what you see on our slide here, that allows you to set your audio for either computer audio or for dial-in on the phone. At present, all attendees are muted to reduce background noise, but we would like to hear from you. You'll notice that the webinar control panel has a box for questions. If you enter your questions there and click send, we'll collect those, and at the end of the webinar, we'll go through and address any questions that we receive. You'll also find in the control panel several downloadable files, including flyers on Swan's offering of sodium analyzers, a white paper on caring for sodium analyzers, and a multi-page brochure covering our complete line of analyzers for the power industry and for steam cycle chemistry. So, our speaker today is Randy Turner, Technical Director for Swan Analytical USA. Prior to joining Swan, Randy was a chemist at Southern Company for over 33 years, first as a plant chemist for 17 years, and as corporate chemist for 16 plus years, supporting their entire fleet of fossil plants. He's been an active voice on cycle chemistry issues, including time as chairman of EPRI's Cycle Chemistry Program, a member of the ASME Water Management Committee, chairman of the ASME Power Plant and Environmental Chemistry Committee, and ASME PTC 19.11 Committee on Sampling, Sample Conditioning, and Monitoring. Most recently, after numerous years as a member of the International Water Conference, he became a member of the Executive Council for IWC earlier this year. I'm sure you're going to enjoy hearing from him, and we look forward to an informative presentation. Randy, please take it away.
Thank you very much, Dominic. Good morning, everyone. I want to talk to you today about a very important topic which is near and dear to me and all of us power plant chemists. We're going to talk about sodium. Some of the topics we'll discuss is why do we measure sodium? Why do we measure sodium continuously? We'll talk about sodium and reference electrodes and some of the design and issues you can incur based on the nature of the sodium electrode and reference electrode. We'll talk about sample conditioning, which is critical for accurate monitoring of sodium. We'll briefly discuss the effective temperature on the measurement of sodium. Then we'll touch base on a couple of maintenance items that are very important, such as etching of the sodium electrode and calibration. And then we'll close with a discussion of some of the potential issues which you may incur. So why measure sodium? Sodium can be in the form of sodium hydroxide or corrosive salts such as sodium chloride. Sodium is everywhere. It's on the dust particles in the air. And in the steam water cycle, it can cause stress corrosion, cracking, and corrosion fatigue of the stainless steel components, such as the superheater, reheater, and steam turbine. Sodium hydroxide has probably damaged more steam turbines than any other compound. And give you an example of just how much sodium flows through the steam water cycle on an annual basis. At a concentration of 1 part per billion, there's 8.76 pounds of sodium will flow through the cycle over the course of a year for every 1 million pounds of steam flow. So as you can see, that's quite a bit of sodium, which allows for the deposition of sodium on the steam turbine during operation. And sodium can also cause underdeposit corrosion in boiler, and specifically caustic gouging, leading to boiler tube failures. Why measure it continuously as to by grab sample? Well, it provides early detection of carryover into the steam. It can reduce the risk of stress corrosion, cracking of the superheater, reheat, and turbine components, as well as reduce the risk of corrosion fatigue of the superheat, reheat, and turbine components. It provides early detection of contaminant ingress into the boiler or steam water cycles, thereby helping you to reduce the risk of caustic gouging, reduce risk of hydrogen damage due to accumulation of corrosive salts, and also reduces the risk of forced outages due to internal corrosion. What you see in the two pictures here is the result of significant sodium deposition on the steam turbine blading and disc. As you can see, they are severely pitted, requiring extensive, expensive, and lengthy repair. Let's talk a little about stress corrosion cracking. What you see here is a picture of the rotor and disc and the turbine blading, which fits into the disc. Deposition of sodium salts can lead to pitting, which can cause cracks, intergranular cracking or stress corrosion cracking in these components, as you see in the center picture in the steeples of the disc. These can lead to catastrophic failure, in which the steam turbine blade comes loose and causes significant catastrophic damage to the steam turbine. Therefore, steam purity is critical. What you see in this picture is caustic gouging damage to a boiler tube. You have accumulation of sufficient concentration of sodium hydroxide that attacks the carbon steel and looks almost as if you took an industrial grade ice cream scoop and scooped out some of the metal.
Okay, we're going to pause for a brief poll. You've seen a little bit of the types of damage that sodium can do in a steam cycle system. I'd like to get your input right now. Are you monitoring sodium currently in your plant? Where are you monitoring at? Please feel free to click on any or all of the answers, and we'll give it a couple of seconds, and then we'll share those results with you, get a feel for what our audience is currently doing. Okay, we've got about a third of our, actually 40%, 50% of our attendees have answered. We'll pause just a couple more seconds to let folks click in and get their votes counted. Okay, I think we will go ahead and close this, and we'll share the results with you. So what we're seeing is that the most common place to monitor sodium is in the condensate and feed water, and also in the steam. But we're also seeing a number of people that are either checking makeup water or boiler water, and a very small portion that are not checking sodium at all. So I'll hand it back to Randy, and we'll carry on with a little bit about how to maintain your sodium analyzer.
Thank you, Dom. What you see in this last picture is an example of under-deposit corrosion. And this occurs when you have sufficient deposit growth in the boiler tube and you have accumulation of corrosive salts under that deposit, causing corrosion of the base metal. Now, take a moment to discuss the typical points within the steam water cycle in which sodium is measured, as well as other parameters. The steam water cycle process begins with the makeup water, and it is very common to measure sodium in your makeup water, as well as some other very important parameters. Then the makeup's introduced to the hot well, and there's also significant potential for contamination of the high purity condensate in the hot well due to cooling water ingress. Therefore, monitoring of sodium in the hot well is strongly recommended. If you have condensate polishers, there's potential, particularly with deep bed polishers, for sodium slippage during transition from hydrogen to ammonia cycle. Therefore, measuring sodium is recommended. Then you will also typically monitor sodium in the feed water, as well as the boiler water, and particularly in the steam cycles, such as saturated steam and your live or main steam. Let's talk a few moments about sodium electrodes. What you see in this picture is our sodium electrode, and it has a special glass membrane that rejects the introduction of most ions. However, as you see in this graphic to the right, ions such as hydrogen, silver, of course, sodium, potassium, ammonia can penetrate this glass membrane. And the selectivity or the sensitivity of these various ions by the electrode are quite significant. For instance, the sodium electrode is 100 times more sensitive to hydrogen ions than sodium. It's 10 times more sensitive to silver ions than sodium. And 1/10 as sensitive to potassium and 1/100th as sensitive to ammonia as it is sodium ions. And this is very important to remember, because if you have a source of hydrogen or silver ions, they can cause significant interference in the measurement, causing a positive bias. What you see in this picture here is a sodium measurement system in which you have this sodium electrode here and a reference electrode. And the significance of this, I want to point out, is in the design of our reference electrode. As you saw in the previous slide, use of silver ions can cause a positive bias. It's 10 times more sensitive to silver than sodium. Therefore, we do not use a silver chloride reference electrode. We use a mercury-based or calomel reference electrode. And the design of this, instead of using a porous junction or a frit, we use a tapered ground glass junction, sleeve junction, which has a hole in it with a sleeve, and you snug the sleeve on the body of the reference electrode, and it allows the proper amount of reference electrolyte to flow into the sample. The advantage of this design is if it becomes clogged and stops flowing, it's easy to clean and remove the deposits and put it back into service, as compared to a porous junction, which oftentimes you have to replace it once the junction becomes clogged. And what you see in this picture here, this is actual picture of our reference electrode with this ground glass sleeve. And speaking of reference electrodes, there's typically 3 types of reference electrodes. I've mentioned 2 of them already, is the silver chloride, which increases the risk of positive bias, the iodide or Ross electrode, and the calomel or mercury-based reference electrode, which we use. As I mentioned, the issue with the silver chloride is if the silver ions are exposed to the measuring electrode, it will cause a significant interference or positive bias. The iodine or Ross electrode can experience significant drift if you have sample pH and sample flow fluctuations. The calomel reference electrode does not cause an interference and is very stable and provides low drift. Therefore, calomel reference electrode is the more stable of the reference electrodes. What you see in this table here is where we compared the drift of the iodide or Ross electrode and the calomel electrode. We varied 3 parameters: sample flow, sample pH, and temperature. And as you can see, when we varied the sample flow, the Ross electrode would drift 7 to 15 millivolts, whereas the calomel would only drift 1 to 2 millivolts. And the actual design of the Swan sodium analyzer has a constant head chamber, therefore you don't actually experience sample flow fluctuations due to the fluidics design. When we varied the pH, we saw a significant drift, approximately 10 millivolts of the Ross electrode, and it is maximum of 1 millivolt for the calomel. When we changed the sample temperature from 20 to 40 degrees centigrade, both electrodes drifted approximately 7 millivolts. So why is this significant? Well, if you have all three of these parameters fluctuating at the same time, you can have as much as 32 millivolts drift with the Ross electrode, whereas with the calomel, the maximum of about 10 millivolts. And why is that significant? Well, it's significant when the millivolt potential change going from 1 ppb to 10 ppb of sodium is 59 millivolts. If you have a drift of 32 millivolts, then that's over a 5 ppb drift. Therefore, for the fact that steam purity is critical, accurate measurement of sodium is critical as well. Sample conditioning, why is that important? Well, as we mentioned earlier, sensor is 100 times more sensitive to hydrogen than to the sodium ion. Therefore, hydrogen ion concentration must be greatly reduced. And this is accomplished by adding a reagent to increase the pH to between 10.5 and 11.5. And this reagent is called diisopropylamine, or commonly referred to as DIPA. If the pH increases above 12, then you can actually experience interference from the reagent itself. Therefore, for accurate measurement of sodium, continuous pH monitoring and control is essential. There are different methods of reagent addition. We use the vapor phase of the reagent to increase the pH of the sample directly rather than diffusion tubing, and we use two means of reagent introduction. We use a passive method in which there is no air pump, and then we use an active method in which we use an air pump. Many manufacturers use diffusion tubing, in which the sample flows through the tubing, which is submerged in the reagent itself, allowing the reagent to permeate through the diffusion tubing into the sample to increase the pH. The common issue with this method is that the permeability of the diffusion tubing rapidly changes, thereby once you put the new tube in service, the permeability decreases, therefore the sample pH after addition of the reagent is decreasing over time as well. What you see in this picture is a example of a passive alkylation method. The sample flow comes into the constant head chamber, fills it up to the appropriate level, then flows into the fluidics of the measurement system. It has a Venturi effect, pulling a vacuum on the reagent bottle and the air supply through the filter. So the air flows through the filter into the reagent bottle, mixes with the DIPA fumes, and air in DIPA is introduced in the sample, thereby increasing the sample pH. For this method of alkalization, the process or steam water cycle sample pH needs to be approximately 7 or greater. This method will adjust the pH to a range of 10.5 and 11.5. And it is important to maintain proper pH control in the proper range to measure low sodium values. Otherwise, you'll get a positive bias from the hydrogen ions. What you see here is an example of an active alkalization process, whereby you have an air pump that is pulling air through the filter, introducing it to the reagent bottle, mixing with the vapor phase of the reagent, and then introduced into the sample stream to increase the pH into the proper range. With this method of alkalization, the sample pH must be equal to or greater than 2 for samples such as primary cation effluent in the makeup water plant. The pH again is adjusted to 10.5 to 11.5, and again, pH control is critical to measure low levels of sodium. And as mentioned earlier, some manufacturers use diffusion tubing, which embrittles, reducing the permeability, thereby experiencing a reduced alkali sample pH over time. What effect does temperature have on the measurement of sodium? Well, as you see in the table to the right, you have the slope of the electrode at various temperatures. Excuse me. The electrode slope increases with increasing temperature, as you can see. So at 25 degrees centigrade, the slope of a perfect electrode is 59.16 millivolts, which means the millivolt potential of the electrode changes 59.16 millivolts per decade change in sodium concentration. However, at 15 degrees centigrade, it only changes 57 millivolts. And at 35 degrees centigrade, the millivolt change is 61 millivolts per decade change. Therefore, measurement of the sample temperature with temperature compensation to compensate for the fact that temperature has on the slope electrode is critical for accurate sodium measurement. Let's talk a few moments about some maintenance activities that are critical to maintain a well-performing sodium monitoring system. Etching. Etching removes inactive and fouled layer of glass on the measuring electrode. It also replenishes sodium ions lost in that special glass membrane when operating in low sodium samples for extended period of times. So what you see in the graph here is the response of an electrode that is in need of etching. It's introduced to about a 25 ppb sodium standard. And as you can see, once it's introduced here, after 10 minutes, it's only reading about 18 ppb, and it takes an hour or longer before it reaches the plateaus out in response to the introduction of the spike. Once the electrode is etched and the same standard concentration is introduced, you see in the green here a very rapid response. In less than 10 minutes, it is reading the value of the standard introduced. Therefore, etching is critical for quick, accurate response of the sodium electrode. Next, we'll talk about calibration. And what you're doing there is you're introducing two standards. The second standard is 10 times the concentration of the first. In this case, we use a 200 and a 2000 ppb standard. And when you do the calibration, the analyzer determines the offset here, which is influenced by the reference electrode, and it determines the slope of the electrode, which is the millivolt change per decade change in sodium concentration, and the theoretical value at 25 degrees centigrade of a well-performing sodium electrode is 59.16 millivolts per decade change. Now, the isopotential pointer offset, the theoretical offset is plus 125 millivolts plus or minus 20 millivolts for the Swan reference electrode. Deviations from this pointer are caused by a number of factors, such as small differences in materials, workmanship variations on the sensors because they're handmade, and aging of the sensor system. Also, loss of reference electrolyte if it is not flowing due to build up of the potassium chloride crystallizing at that ground glass junction, or if the reservoir is empty, then that will also affect the offset. The slope of the electrode. An ideal sodium electrode couple has a millivolt change of 59.16 millivolts per decade at 25C. So what that means is there's a 59 millivolt change when the sodium concentration changes from 0.1 to 1 ppb. There's another 59 millivolt change when the concentration of sodium increases from 1 to 10 ppb. You also need to monitor your sensor response delay on a day-to-day basis. That will allow you to determine if the electrode is experiencing the phenomenon called sodium depletion, in which it is slow to respond and is in need of etching to increase that response time. The response time will change over time, particularly when monitoring very low sodium samples. And to improve this, it must be etched always before calibration. So what are some of the potential issues that you may experience? If the reagent or DIPA is too low or empty, you'll experience low pH of the alkali sample and high sodium readings due to the hydrogen ion interference. Reference electrolyte empty or not flowing, you will experience unstable readings and slow response. Sodium depletion due to operating a very low sodium sample for an extended period of times. The sodium response is very slow, therefore etching and calibration electrode will rectify this situation. If the slope is out of limits, you can etch the electrode and recalibrate. If this does not resolve the issue, then replacement electrode is recommended. If the offset is out of the limits, this is due to the reference electrode. So you need to ensure the reference electrolyte is flowing and that you have electrolyte in the reservoir. And if all of your efforts to resolve this are unsuccessful, then you will need to replace the reference electrode. So in summary, some of the issues or headaches that you may experience with a sodium analyzer, as well as the Swan approach to resolve that issue, saving you operating expense, are things such as low pH. We measure the sample after addition of the reagent so that you will be assured that the proper pH is achieved in the monitoring system. Clogged reference electrode. We use the ground glass sleeve as to a opposed to a porous junction, which allows you to easily unclog the reference electrode. Diffusion tubing, it embrittles over time. Swan does not use diffusion tubing. We just use the vapor phase. Drifting, the reference electrode chosen for our monitoring system eliminates major causes of drift, such as fluctuations in pH, temperature, and sample flow. Electronic drift, all instruments experience electronic drift. All of the Swan analyzers have built into the motherboard a process called electronic drift stabilization, which minimizes our electronic drift. Cost of the air pump. We do not use an air pump for the SodiumP, which is the passive alkalization method. Grab samples. Integrated into our design is an easy to use grab sample measurement system. Instrument failure. All of our analyzers have a 3-year warranty, therefore it minimizes your risk and expense for 3 years. So at this time, I'm going to turn it over to Dom.
Thank you, Randy. So we do have a few questions, but before we get to your questions, we're going to hit you with one more question of ours. Hopefully, from seeing this presentation, you've gained an appreciation for the importance of sodium monitoring, and just wanted to see what it looks like out there. If you're looking to purchase a sodium analyzer in the coming year, Swan does have a really solid offering, and we'd be happy to help you. So feel free to hit us with an answer there, and we will close that up in just a minute or two and get back to the real questions. Okay, so David wrote us a question regarding calibration. I think in our slide, Randy, we showed calibration at 200 and 2000 ppb. David is calibrating at 100 and 1000, but their samples are generally less than 0.5 ppd, and ppb, excuse me, and they have an action limit of 2 ppb. Would there be any benefit from David using some different calibration standards, perhaps a 10 ppb and 100 ppb?
It's a very good question. It's not necessary. I mean, can they do that? Yes. The risk they run is the potential error making very low ppb sodium standards, such as a 10 and 100, is much greater than when making a 100 or and 1000 or 200 and 2000 ppb standard. So you have greater risk of errors being introduced through the calibration process when using those much lower standard concentrations. And also, since it's linear, then it's not necessary. You get very accurate sodium measurements at the levels David referenced when you calibrate with the 100 and 1000 and even the 200 and 2000 ppb standards.
Okay, thank you, Randy. We have a second question. We have a attendee today that's having some problems with their sodium analyzer. They're using an analyzer that has a diffusion tubing delivery system, and they're getting some water leakage into their DIPA. Could you maybe speak a little bit to the problems that might occur with water in the DIPA? I think I know the answer, but could you clarify what Swan would suggest in that type of situation?
Well, that is always a potential problem. It could be leakage through the diffusion tubing, small pinhole, or it could be leaking around the connection point of the diffusion tubing to the cap of the chamber. The water is leaking around that seal. And the issue with that is you're diluting your DIPA, therefore you're not going to get proper alkalization, especially as the water continues and dilutes the DIPA.
Okay, thank you, Randy. So the answer there, correct me if I'm wrong, but the answer is try to get an analyzer that doesn't rely on diffusion tubing?
That is definitely a good option. Has always been my preference, even before I joined Swan, because you eliminate the issues with diffusion tubing because it does embrittle over time. The permeability decreases, therefore your sample pH is decreasing over time, and therefore with using the vapor phase, you just eliminate all those potential issues.
Okay, thank you. Looks like we've got one more question regarding, oh, okay, we got two more questions. So let's see. This was a question on potassium interference and whether the design of the Swan helps eliminate potassium. Some questions about the flow cell and the half cell design of our sodium measuring chamber. Could you maybe comment on that?
Yes, thank you. Yes, potassium does cause an interference. It has 1/10 the response to potassium compared to sodium. Therefore, if the electrode is exposed to potassium, it will cause a positive bias. The design of the Swan analyzer. Now, we use potassium chloride as our reference electrolyte. To eliminate the potential for interference from the electrolyte, the fluidics of the flow cell for the measurement process is designed such that the sample comes into a chamber which houses only the measuring electrode. It comes into the bottom, fills the chamber up. There's an overflow at the top that flows down to the bottom of the next chamber, which houses the reference electrode, the temperature electrode, and the pH electrode. Therefore, the measuring electrode is not exposed to the potassium from the reference electrolyte in our fluidics design.
Okay, thanks very much, Randy. Another question. This one's regarding sodium and silica. This is from Mike. He mentions that he's been told that sodium can be used as a quasi-measurement for silica, a rate of 3-to-1 under most boiler pressure conditions other than supercritical. Is that accurate? And could you comment on that?
Well, I'm not familiar with that relationship, and my concern in using that type of relationship is there are so many sources of sodium. It can be in your makeup water. There will be trace amounts in your makeup water. There could be trace amounts in the chemistry that you are feeding into your feed water and boiler water, such as your ammonia, or if you're using a reducing agent. Also, if you're using a boiler water treatment such as sodium trisodium phosphate or caustic, those are significant sources of sodium. Therefore, I've never observed in my career a relationship between sodium and silica in the boiler water that I had any confidence in using to say if my sodium is 10 ppb, my silica would be a factor of 3 higher or lower.
Okay, thanks, Randy. And I'll mention, Mike, in the download section, we do have our full line of power analyzers, and we do offer a couple of options for silica measurement that you might want to look at. Feel free to reach out to us if you have some questions. We did have another question for Mike, and that's on sodium readings on steam and condensate. Question is, what is a high ppb number, and what should an action limit be? And then finally, what recommended actions would you have for dealing with high sodium?
Well, the industry limits typically is 2 ppb in condensate and steam as a maximum. Of course, you want to operate as low as practical. Just because the limit's 2 doesn't mean operating at 2 is a good thing. As that sodium value increases, you have greater risk of sodium deposition and subsequent pitting and corrosion. As far as action limits are concerned, if it's in condensate and steam, if it's in condensate, you got a potential contaminant ingress. It could be coming from the makeup, or you can have a very small condenser leak, or other source of contaminant ingress that has sodium contaminated water. If it's in the steam, if it's a drum type boiler, it is coming, could be mechanical carryover or vaporous or volatile carryover due to issues in the steam drum, or sufficient concentration for the operating pressure that some of the sodium is carrying over with the steam. So the response to that is if you can decrease the sodium in the boiler water by blowing down and see if your steam sodium decreases. If it does, then you have to operate your blowdown more to maintain lower levels of sodium in the boiler water to reduce your steam sodium concentrations.
Okay, Randy, it looks like we have one more question. It's from Sumya. She asks, what is the cycle time of each sample measurement, and how many sample lines can one analyzer measure with an external sequencer?
Cycle time will be dependent upon the flow, but it's going to be approximately 3 minutes or so. And the maximum number of sample lines for our analyzer, I can't speak for competitors, is 6 sample streams with our external sequencer. We also have an option for the single line analyzer. You can add the dual stream option, in which you can monitor 2 different sample streams with the one analyzer, depending on your needs.
Okay. Thanks, Randy. One more question. I think this goes back to Mike's question earlier about sodium and silica. If you have a sodium analyzer on your condensate water, do you really need a silica analyzer as well?
Sodium analyzer and silica analyzers are monitoring, as we know, 2 different parameters. Then there's no relationship between the sodium and the silica that is in your steam water cycle, because there are so many different sources of sodium. It can be, like I said, a condenser leak. It can come from your makeup water. Therefore, monitoring the sodium is definitely is recommended by EPRI and IOPS VGB. Silica, most of the people in plant companies in this industry in the U.S. monitor the silica. It is not a required monitoring point by EPRI and IOPS, but due to the issues with increased silica and carryover in the steam resulting in deposition on the steam turbine, which impacts the efficiency of the steam turbine. Most companies, particularly at higher pressures, 2000 psi and above, will monitor the silica and particularly the steam and the boiler water. They typically will also monitor the steam and the condensate as a means of rapid identification of ingress of silica-laden water due to a condenser leak or some other source.
Thank you, Randy. I think that wraps it up for our questions today. If you do have additional questions, don't hesitate to send us a message at our email address or contact your local Swan sales associate. I want to thank you all again for attending today. You will be receiving a thank you email with a quick survey asking for your feedback on today's presentation. And we hope to see you in the future for our next Swan webinar. Thank you again. Goodbye.